Hi folks, here is the video for 4.6, variation of parameters. And so as we begin, let's start with a little bit of what we know. So far in chapter 4, we've talked about solving homogeneous second order differential equations with constant and non-constant coefficients. And we've also talked about how to solve non-homogeneous second order differential equations with constant coefficients. And so what we're going to talk about in 4.6, what's new, is we're going to look at some more non-homogeneous differential equations. All right, so we're looking at those non-homogeneous differential equations. However, we're going to use a different method than we learned previously. Okay, so we're going to take a look at a method called variation of parameters. It's a little bit more formulaic and a little bit more process-based than some of the other methods that we've seen. Okay. So as a friendly reminder, here's sort of where we've been in the chapter, right? So we've taken a look at non-homogeneous second order differential equations. In our constant coefficient situation, we've looked at the method of superposition. And what we're going to take a look at here is this idea of variation of parameters. All right, so being able to compare superposition to that variation of parameters is going to be something that's really important because they solve the same kind of questions, okay, for the most part. We will not be covering that annihilator method, all right, so we're really focused on that superposition and then this idea of variation of parameters. All right, so before we move forward, I'm going to go ahead and write down some important things, all right? So if we have this second order differential equation, let's say y double prime plus p of x y prime plus q of x y, all right, so there's our second order differential equation, but it's non-homogeneous, so we're going to say it equals some function g of x, all right? So if you have that, and we have y1 and y2 are a set of solutions for the associated homogeneous differential equation. So that is y double prime plus p of x y prime plus q of x y equals 0, right? So we're looking at the associated homogeneous differential equation. Then it turns out that the particular solution can be found using the following formula. Okay. And so here's the formula, but before I write it down, I just want us to sort of breathe in, breathe out. It's a long looking formula. It looks more complicated than it is. It does require us to be really diligent about our simplification, our algebra, our calculus, but we can say that y sub p equals the sum of two terms. The first one is negative y1 times the integral of y2 times g of x over w. Okay, and I'm actually going to write this as the w of y1 and y2 dx plus, for the second term, we switch our y1 and our y2. So plus y2, the integral of y1 g of x over w y1 y2 dx. Okay. Now, what is this w y1 y2, you might ask? And so let's go ahead and define it here. Our w here is our Wronskian, all right, and our Wronskian can be defined as follows. W of any two functions, so we'll say y1 and y2, is going to equal y1, y2. Those are going to be in the first row of this matrix. And then the second row will be y1 prime and y2 prime. We're going to go ahead and find that determinant, and we're going to get y1, y2 prime minus y1 prime times y2. Okay. And so that Wronskian is going to be something that we are able to find. And then we're going to use that as the denominator in these integrals that we have right here. Okay. So we have a few examples for us today. All right, so we have 3 examples. We're going to talk through those, make sure we understand the language behind them and how to apply this process. Okay. All right, so practice number 1, find the solution for y double prime minus 2y prime plus y equals e to the x over x squared plus 1. Okay. And so we're going to begin by going ahead and finding the y sub c. All right, so finding y sub c will allow us to find the y1, y2 that we're going to need for our Wronskian. Right? And so we're going to solve this associated homogeneous differential equation using our characteristic equation. All right, because I have constant coefficients, I can use that characteristic equation. I'm going to use the letter m today just because I'm feeling it. So we'll do m squared minus 2m plus 1 equals 0. We find that this factors into m minus 1 squared equals 0, which means that we have m equal to 1. Right? Now notice this happens 2 times, so we can say that this is real and repeated roots. This allows us to go ahead and find our y sub c. So we'll look back into our notes to find out which form this is, and we'll end up with c1 e to the 1x plus c2 x e to the 1x. And we don't have to write the ones because they're ones. So we could simply write c1 e to the x plus c2 x e to the x. Okay. Now, what do we have here? In this process, this is going to be our y1. And the x, e to the x, is going to be our y2. All right, so we'll just write y1 here and our y sub 2 here. And if you switch them by accident or you write them in a different order, that's okay. Everything should sort of clean itself up as you simplify. Okay. All right, so once we find our y sub c, we're going to find y sub p. But we're going to break this down into 2 different steps. And so first, we're going to find the Wronskian. All right. So let's go ahead and write down that equation. W equals y1, y2, y1 prime, y2 prime. And our y1 is e to the x, which means y1 prime is e to the x. And our y2 is x e to the x. And we're going to need product rule to find our y2. So we'll get e to the x plus x e to the x. Now to find that Wronskian, we're going to take the product of these 2, and we're going to subtract the product of the other 2. So we get e to the x times e to the x plus x e to the x minus e to the x times x e to the x. And let's see what that gives us. We're going to end up with e to the 2x plus x e to the 2x minus x e to the 2x. Now notice that these last 2 terms are equal, but have different signs. So they're going to reduce to make 0. And our Wronskian for this first example will be e to the 2x. All right, now I'm going to go ahead and color this yellow. All right, so we found our Wronskian, and that we're going to use in this formula as our denominator. Okay. Now, I think while we're here, let's maybe note that our y1 will be here and here, and our y2 will go here and here. And last but not least, our g of x, which is just the non-homogeneous side of our equation, in this case is e to the x over x squared plus 1. That's what we're going to multiply in to that numerator in both integrals. All right, so the second step in finding our y sub p is we're going to use that formula. Okay, now I'm going to go ahead and copy that formula down because I know that it's hard to remember like what we're going to plug in where. But keep in mind, this is an open notes exam, so you don't need to memorize the formula. You just need to be able to find it and use it appropriately. So our y sub p will equal negative y1, the integral of y2 times g of x over the Wronskian dx, plus y2, the integral of y sub 1 g of x over the Wronskian times dx. Now I'm going to color code this real quick so we can make sure that we know we're plugging things into the right place and that we are simplifying correctly. That's probably the hardest part. Okay. So we've got 4 things that we're substituting in. And so let's see, our y sub 1 is e to the x. So we'll have negative e to the x times the integral of y2 is x e to the x times the Wronskian, or the g of x, which is e to the x over x squared plus 1. All of this is over our Wronskian, which is e to the 2x. Seal it off with the dx. All right, so we've got our Wronskian here. We've got our y sub 1 out here, our y sub 2 over here, and our g of x here. Okay. This is a good place to check your work just to make sure you've plugged in everything correctly. But let's go ahead and plug in the rest of the second term. We're going to get plus x e to the x, the integral of e to the x times e to the x over x squared plus 1 over e to the 2x dx. So we have our g of x, we have our Wronskian, we have our y sub 1, we have our y sub 2. Okay. Now I know it's been a really long time probably since you've seen integrals like this. It's probably been since like Calc 2. So we just need to be really careful at working through all the steps, all right? And so let's begin. We get negative e to the x times the integral of these numerators here are going to become x e to the 2x times 1 over x squared plus 1 all over e to the 2x dx plus x e to the x, the integral of, well, these numerators combine to make e to the 2x, and we're going to multiply that by 1 over x squared plus 1 all over e to the 2x dx. Now at this point, we should be able to cancel quite a bit, all right? Now we want to be really careful about our cancellations. But I see here that I have e to the 2x in the numerator as well as the denominator, so those are going to go away. But what I still have is an x times 1 over x squared plus 1. And so before I simplify the other term, let me go ahead and gather what I have left in this first term. I have negative e to the x times the integral of x over x squared plus 1 dx. And I'm going to make a note to myself here that I'm going to be able to use u sub to figure out this integral. And the reason I know to use u sub is because the derivative of x squared plus 1 is 2x. And that'll help take care of this x in the numerator here. Okay. But before we solve that one, let's see what cancels in that second term. So this e to the 2x in the numerator is going to cancel with this e to the 2x in the denominator. And I'm going to have add x e to the x times the integral of 1 over x squared plus 1 dx. Now this small change, the fact that this one has a 1 in the numerator and this one has an x, means that we're going to use a different technique. And in fact, this is our inverse tangent integral. And so we'll be able to use that and we don't need to use u sub. All right, I'm going to go ahead and set up the u sub for this first term. We're going to let u equals x squared plus 1, du equals 2x dx, and I'm going to divide both sides by 2. So everywhere I see x dx, I'm going to be able to substitute in du over 2. And this is going to give me, negative e to the x times 1/2. So I'm going to go ahead and pull that constant right out, the integral of 1 over u du plus x e to the x integral of 1 over x squared plus 1 dx. All right, so let's integrate. We're going to go ahead and end up with negative e to the x times 1/2 natural log of x squared plus 1 plus x e to the x times the inverse tangent of x. You're welcome to leave it like that. All right, so we found our y sub p and we found our y sub c. And our last step here is to write a general solution. And what we mean by that is we want to find y, not y sub c or y sub p, but we can go ahead and add those together. And so our y sub c was c1 e to the x plus c2 x e to the x. And our y sub p is going to be this whole long clump. So minus e to the x over 2 natural log of x squared plus 1 plus x e to the x times inverse tangent of x. Okay. So we'll go ahead and put a box around this. When we say solve or find that general solution, we need to find the sum of our y sub c and our y sub p. Before we move on to the next question, let's just get this all on one page for you so you can pause here if you missed anything along the way and you want to go back and figure that out. All right, so let's go ahead and move on to example number 2. Okay, and so this right here, we have solved this second order non-homogeneous differential equation with constant coefficient. And so knowing that we can use variation of parameters, we're going to go ahead and find our y sub c, just like we did in the first problem. And then we're going to find our y sub p, and then we're going to add them together to get our general solution. And so we're going to go ahead and say we have a characteristic equation of 4m squared plus 36 equals 0. We see that this can be factored into 4 times m squared plus 9 equals 0, which 4 doesn't equal 0. So only m squared plus 9 can equal 0. So we get m squared equals negative 9, and we get m equals 0 plus or minus 3i. Now I'm writing the 0 here. You don't need to write the 0. You can just say plus or minus 3i. But I want to make sure that we understand there is a 0 there. So when we plug this into the sort of general form for this solution, we want to make sure that we have e to the 0, not e to the 1, okay? I know it can get confusing with like the invisible numbers in math, and we're just supposed to know all these invisible numbers. So if it helps you to write out that 0, so you remember it's not a 1, that's not a bad thing to do. So this gives us the general form y sub c equals e to the 0, c1 cosine of 3x plus c2 sine of 3x. Now, e to the 0 is only 1, so I can simplify this to c1 cosine 3x plus c2 sine 3x. So we found our y sub c. Now we're going to go ahead and find our y sub p. We're going to use the same 2 steps. We're going to find our Wronskian. And then we're going to plug it into that big formula we had at the beginning to find our y sub p. All right, so if I were to continue with the color coding, I would say that this sine 3x is my y sub 2, and my cosine 3x is my y sub 1. And so let me label those. We have y sub 2, y sub 1, and the other one, the second one, is our y sub 2. All right, so the Wronskian is defined as y1 and y2, right? So sine 3x, cosine 3x in that first row. And then we need to take our derivative to find our second row. And we need to use chain rule for both of these. So we're going to get negative 3 sine 3x. And then in the second one, we'll have 3 cosine 3x. We're going to find our Wronskian by multiplying this sort of main diagonal and then subtracting the product of the non-main diagonal. And so that'll give us 3 cosine squared 3x minus a negative 3 sine squared 3x. Notice that this minus minus is going to make a plus. And then we actually have 3 times cosine squared 3x plus sine squared 3x. And we might remember that this inside the parentheses is one of our Pythagorean identities. And it turns out that cosine squared plus sine squared goes to 1. And so our Wronskian in this case is just the number 3. Okay. All right, once we find our Wronskian, we're going to find that y sub p. And I'm going to write that big old formula out again, and just so we can color code a little bit and think about what goes where. So y sub p equals negative y sub 1, the integral of y sub 2 times g of x over w dx, plus y sub 2, the integral of y1 times g of x over the Wronskian dx. And so we know from the last line that the Wronskian over here in the denominator is going to be 3. And we know from above that our y sub 1 is going to be cosine 3x. And we know that our y sub 2 is going to be sine 3x. And our g of x is way back in the original problem. And in this case, it is 1/4 cosecant 3x. Okay. All right, so let's go ahead and plug everything in. We're going to be really careful about the substitutions. We'll get negative cosine 3x times the integral of sine 3x times cosecant 3x. And it is cosecant times 1/4. So I'm going to go ahead and stick that 1/4 out in the front as a constant. Okay. And I'm dividing all of this by 3 dx. And so we have our g of x sort of split here. Just because I can take out a constant, it makes things a little bit simpler. I have my y sub 1. I have my y sub 2. And I have my Wronskian. And now if I substitute in the second term, I'm going to get plus sine 3x integral of cosine 3x times cosecant 3x all over 3 dx. And just like before, I got to take care of that 1/4. So I'm going to go ahead and multiply in that 1/4 as a constant. Okay. And if we were to finish our color coding, we've got our Wronskian here. Our g of x, once again, is sort of split. The y sub 1 is inside the integral this time, and our y sub 2 is outside the integral. All right, now as we simplify, it might be really important to remember that cosecant is 1 over sine. Okay, so cosecant of 3x is actually the same as 1 over sine of 3x. And so I'm going to do a few things at one time. I'm going to go ahead and take this 3. I'm going to factor it out as well. So I'm going to have a 1/12 out in the front. Okay, so I'm going to keep this negative cosecant 3x times 1/12. And I'm going to rewrite this integral here as sine of 3x times 1 over sine 3x. And as soon as I write that out, I bet we can see that these are going to reduce, and I'm only going to have a 1 inside that integral. All right, let's take a look at the second one. How does that one clean up? I'm going to do the same thing. I'm going to bring this 3 out to the front. So instead of a 1/4, I'll have a 1/12. I'm going to write this as cosine 3x times 1 over sine 3x dx. And now let's see what we can do. Okay. So I end up with negative 1/12 cosine 3x times the integral of x, which is, or integral of 1, which is just x, plus I have 1/12 sine of 3x. And in order to do this integral, I'm going to use u sub. Okay. And so let's make ourselves a little bit of room out here. So we'll write u sub, and we're going to let u equal sine 3x, du equals 3 cosine 3x dx. I got to divide both sides by 3. And now everywhere I see that cosine 3x dx, I can replace it with du over 3. And so I'll have that 1/12 sine 3x times 1/3 the integral of 1 over u du. All right, we are almost done with our integration here. We're going to end up with negative 1/12 x cosine 3x plus, I'm going to go ahead and make this 1/12 and 1/3 into a 1/36. So we'll get 1 over 36 times sine 3x. The integral of 1 over u is the natural log. So I'm going to have natural log of sine 3x. And this is my y sub p. And so to finish off our question, we're going to go ahead and for number 3, we're going to write our general solution. And so we get y equals our y sub c, which is c1 cosine 3x plus c2 sine 3x. It's our y sub c, plus this whole big clump, which is our y sub p. And hooray, we have our general solution. All right, I'm going to go ahead and put this all on one page again for you in case you want to pause the video here. That way you can see the entire question on one page. All right, now we're going to go ahead and work through our very last example, example number 3. Okay. All right, so example number 3 says, solve this second order non-homogeneous differential equation. And we're actually already given our y sub c, okay? So the work here is really in practicing to find the y sub p part, all right? And so we're gonna take a step, what I'm gonna call 0.5, so a half step, and we're gonna go ahead and divide by x. The reason I'm saying divide by x is because x is the coefficient for that y double prime. In other words, we want to turn this into quote unquote standard form where that y double prime has a coefficient of 1. So we'll end up with y double prime minus x plus 1 over x y prime plus 1 over x y equals, let's see, x squared divided by x gives me x. All right. Now, once I've divided through, this is what we will use for our g of x. That x will be our g of x. All right, we're going to go ahead and find our y sub p. We're going to find our Wronskian first. And we know that the Wronskian will be defined as our y1, y2 in the first row, and then the derivatives of those in the second row. And so where do we get that information? Well, this e to the x is going to be my y sub 1, whereas this x plus 1 is going to be my y sub 2. So we can say we have e to the x and then x plus 1. We take our derivative, we get e to the x and 1 in that second row. We're going to go ahead and take the product along the main diagonal, and we're going to subtract the product along the non-main diagonal. And we'll obtain e to the x minus e to the x times x plus 1, which is going to be e to the x minus x e to the x minus e to the x. Whew, that's a lot of e to the x's. The first one and the last one will cancel, and we will get a Wronskian of negative x e to the x. And I'll go ahead and color this in the yellow. This is what we're going to use as the denominator in those integrals. All right, let's go ahead and write out that big long formula again. I know it's a lot of writing, but I feel like every time I write it, it makes it a little bit stickier in my brain. So y sub p equals negative y sub 1, the integral of y2 times g of x over the Wronskian dx, plus y sub 2, the integral of y sub 1 g of x over Wronskian dx. So we've got our Wronskian that we're going to substitute in here. We've got our value for g of x, which we want to sub in there. We've got our y sub 1s, which are going to go here. And we've got our y sub 2s that are going to go here. And just like all the other ones we've done, we want to be really careful about substituting things in the right place. So we will get negative e to the x times the integral of x plus 1 times x, because that was my g of x, over the Wronskian, which is negative x e to the x dx. Let's make sure we plugged in everything in the right place before we move on. Okay. And now we're going to plug in terms for the second one. So y plus, or y2 is my x plus 1 times the integral of e to the x times x all over negative x e to the x dx. This is my Wronskian. This is my g of x. This is my y sub 1. And this is my y sub 2. Let's go ahead and simplify. We're going to be really careful as we do so. And so I might notice in the first integral that this x in the numerator and this x in the denominator are going to cancel out. That leaves me with negative e to the x times the integral of x plus 1 over e to the x dx. Plus the second one, I'll have my x plus 1 in the front, but let's see what reduces. This x and that x, this e to the x and that e to the x. And so I actually have, and let's be careful about this negative sign, right? I actually have the integral of negative 1 dx. Now this second integral, I'm not worried about. I know we can integrate that. But the first one over here, this x plus 1 over e to the x, it probably would be nice for us to go ahead and substitute, all right? So, or not, we're going to simplify a little bit here. And so what I mean by simplify is we're going to split this into two separate fractions. X over e to the x plus 1 over e to the x. It's a nice trick to have, that when you have one term in the denominator and a bunch of terms in the numerator, you can split it into a whole bunch of fractions. And I think this one is simple enough, that second integral, that we can go ahead and integrate that. So we'll have plus x plus 1 times a negative x. All right, so what techniques do we need to integrate these two? Well, might be better if we rewrite it one more time. So negative e to the x integral of x e to the negative x plus e to the negative x dx. So we can see from here, if we think all the way back to Calc 2, that this x e to the x, we're going to need to use integration by parts. And this second one, e to the negative x, we can just use u sub. Right? So the u sub, I think we can sort of do in our heads, but let's make sure we understand how to do the integration by parts setup. So u equals x, du equals dx, dv equals e to the negative x dx, and v would equal negative e to the negative x. And so when we use our integration by parts, we get negative e to the x. From our integration by parts, we'll have u times v minus the integral of v du. All right, so these two terms come from this first term. And now I have to integrate the e to the negative x, which will just be negative e to the negative x. And I still have this minus x, x plus 1 afterwards from that second integral. All right, I think we're getting pretty close here. We've got a negative and a negative, that makes it positive. So x and e to the, let's see, x plus negative x. What is that going to give us? Well, x times negative x is going to give us e to the 0. And then let's do the next part very, very carefully, okay? We're gonna go ahead and say that this minus and this minus make a plus. However, we have this negative out here. So negative e to the x. The integral of e to the negative x is negative e to the negative x. And then we have negative e to the x minus or times negative e to the negative x. So we get plus 1. All right, negative e to the x times negative e to the negative x. I'm going to add my exponents. I'll get 0. So e to the 0 is just going to be 1. All right, we are in the home stretch. Let's see what we have. We have x, we have a negative and a negative, which makes it positive. And we have e to the 0 again, so plus 1 minus x times x plus 1. We're going to end up with x plus 2 minus x squared minus x, which will give us negative x squared plus 2. Okay. I think I made a sign mistake in my first answer. So if you're looking at those notes, I'll go ahead and update those so that it reflects these changes. All right, last but not least, whoops, we're going to write our general solution. And keep in mind, they already gave us the y sub c, which is why we didn't have to find it. And we end up with y equals the y sub c that they gave us plus the y sub p. All right. And so before I finish this video, let's go ahead and zoom in so that all of this is on one page for you. And if you find any mistakes in here, please let me know. It is entirely possible, but I would be happy to clarify that. All right, thanks folks, have a great day.